All right, chapter 16. This topic is on solubility, and afterwards, an influencer of solubility is complex ion equilibrium. Right, this is going to be an extension of our discussions of equilibrium. Right, so when we went through that chapter, I gave you forewarning that it was going to, that's irritating, that equilibrium was going to come back. And it did in acids and bases, and now it's going to come back in solubility. Okay. So turn this on. Maybe once I get rolling, it'll behave itself. And maybe it won't. Is that it? No. I don't know what the problem is. Hopefully that's not part of the recording. All right. So what do we mean by flashing lights? Hold on a second. Let's see if I can settle this thing down. Let's restart. Maybe it's in the projector. Okay, let's restart it. Have to do its warm-up routine. That's a red light. There we go. Lamps on. There we go. What they should have done was put that thing up here. It'd been much nicer. No, it's not going to behave. Well, I guess we're going to have to make do. So direct your attention over here. So what do we mean by solubility equilibrium? When we initially discussed equilibrium, and from then on, we had these K values and they had subscripts. And the subscript was a clue to what the K meant. In this case, it's got an SP on it, which means solubility product. All right, for this example, which is a solid, we're trying to put it in solution. And we're going to stick to aqueous solutions here. We can produce bismuth with a 3+ charge in aqueous solution. And plus oxygen. No, sulfur. I'm sorry. Why did I put oxygen there? Sulfur. Sulfur. 2- charge. Okay, so we get 3 sulfurs and 2 bismuths out of that dissolution. Prior to this, in our first semester, I guess, we talked about solubility in terms of absolutes. In other words, it is soluble or it's not soluble. Remember that chart with the boxes in it? You don't remember that? Where you follow, when you put 2 solutions together, sometimes you get a precipitate. Okay, so how do you tell whether you got a precipitate or not? Well, you use that box, or you use the rules if you got them memorized. and you follow the cations across the top and the anions down the left and where they meet, that tells you if it's soluble. Well, solubility is a continuum. Some things that we listed as not soluble are slightly soluble. Some of them very slightly soluble. But I can't think of a single compound that doesn't go into solution partially, or to a very limited extent at the least. And so now we're going to tackle the middle ground between soluble and not soluble. Okay, so this is our expression, and if we write a K value for it, then we take the bismuth 3+ ion squared, okay, and sulfur 2- ion and cube it. And since that's a solid, it's not there. And solids and pure liquids don't enter into the equilibrium expression. So that's why it's called the solubility product, because it's always a product of the two ions, or more ions. There may be more. Okay. Now, what do we do with it? Remember when we talked about yeah, that's better on your eyes, isn't it? You just look at that one. When we talked about the difference between equilibrium constant and equilibrium position. Well, equilibrium constant is a constant for constant temperature. If the temperature is constant, equilibrium constant is a constant. But the equilibrium position can vary depending on how much of reactants and products you have in the reaction mixture. Okay, so these could be very high numbers, still give you a constant. It could be very low numbers, still give you a constant. That's an equilibrium position. Well, the analogous to that is this K is constant for a temperature, for a given temperature. But the solubility is another factor. How much of that actually goes into solution? Right? And that can vary depending on the compound. The two values, the solubility of this, which we usually give it as a small s, represents the molar solubility. How many moles per liter will this dissolve in an aqueous solution? They can't be the same, because this solubility, if we say just for argument's sake, it's 1 molar, then you would have 2 molar here and 3 molar there, correct? Okay. Then you put those values in here, and that would be squared and that would be cubed. So that would give you the K, but the solubility is not directly related because of these powers and the number of ions that it may produce. Right. That was an extreme example. It's never going to be 1 molar, just for argument's sake. Sometimes the solubility is expressed in mass per unit volume. If you look in a reference book like the CRC manual, you will find solubilities of compounds, and there'll be low solubilities, there'll be very high solubilities, they're all mixed together. They will usually be listed as grams per 100 milliliters of solvent, of water, usually, and at a given temperature. Right, that's useful in the laboratory because then you don't have to go through the molar calculations. But we're going to use molars here because of the way we solve problems. Right, this is molarity because of square brackets. But just to let you know that sometimes the solubility is expressed in grams per 100 mils or grams per liter. All right. So where did we get this expression? Let's try that. All right, so we got sodium phosphate. Yeah, this is a solid, of course, and it gives you 3 sodiums and 1 phosphate in aqueous solution. Okay, if we're going to calculate the KSP, we need to have something to work from. And if we give, let's set up our ice table. I think that's the best way to do it. Right? This doesn't have a value, right? These start off at 0. But if we say this is soluble to a certain molar amount, so many moles per liter, then we can give it a value of S, right? That's the solubility, right? So in this case, if one of these, 1S goes into solution, 3 S's are added over here. And 1S is added over here. Okay? All right. So now we have a 3S here and a 1S there, or just an S. So confuse it. So our K would be sodium. Sodium ions cubed times phosphate ions to the first power. So now we plug in our unknown here. So that would be 3S for the sodium cubed and 1S for the phosphate to the first power. All right, so S cubed times S, the first power is S to the 4th power, right? And then 3 cubed is what? 3 times 3 is 9, and 3 times 9 is 27. Okay. So that's our KSP relationship to the solubility of the compound. That's what they're trying to say. Right here. Okay, that's the relationship between solubility and the K value. Phew. But I don't have to look at that. So far, so good. Worked pretty good. Plus, got little magnets in it. Okay, what's the solubility of silver chloride? So we got to write the compound, silver chloride, correctly, like that, and then set up the equilibrium, which would be silver aqueous with a 1+ charge and chloride. Go 1 to 1 1, and then we write our expression. Let's see. Let's do it over here so we have room for our ice table. KSP then would be simply silver and chloride, just like that. So if we set up our ice table, and these things follow a pattern. So there may become a time when you don't feel like you don't even need an ice table. You can figure it out in your head. If solubility here is some molar amount, and we start off with 0 here, then we're going to have just add an S and add an S. Right? So we have S and S, and the KSP well actually has a value. 1.6 times 10 to the minus 10, right? Okay. So if we plug in S's there, that's S squared, right? Equals 1.6 times 10 to the minus 10. S equals the square root of that. Let's see, maybe I've already done it up here. There we go. There we go. There we go. 1.3 times 10 to the minus 5 is the solubility, and this is in molar. So silver chloride is not very soluble in water. That's why that previous chart listed it as insoluble. Very, very small amount. In fact, there's some even smaller. Some compounds are even smaller than that. Silver phosphate. Now we have a different K for silver phosphate, right? A different KSP. But will that lead to a higher or a lower solubility? Right? The only way to tell is to do the calculation. So we have silver phosphate. Yeah, silver phosphate. 3 of those. And then we have 3 silvers and 1 phosphate. Oops, 3 minus. Okay. So just to be consistent, beginning, the solubility here is our S value. And we start off with 0. Then we're going to add 3 S's for every one of these. Okay, we're going to add 1 S over here. So that means we have 3 S here and an S here. And then we fill in our, I better leave that there. We fill in our K value. 1.8 times 10 to the minus 18 is equal to this one cubed, right? 3S cubed and S to the first power. Okay? Did I do that right? Yeah. Okay. So 3S cubed is 27 and then S to the 4th power. Right, so S is going to be 1.8 times 10 to the minus 18 divided by 27, and then to the 4th root. Good, I did 3 steps at once. I divided this one by that, and then I took, well, 2 steps. And then I took the 4th root of S. Let me split that out a little better. 4th root equals the solubility. Now, all calculators don't have the ability to do more than square roots. So what would we do? Well, let's find out what this value is first. 1.8. See, do I have it up there? No, I just have the answer. Okay. 1.8 times 10 to the minus 18. Okay, divide that by 27. That's 6.67. 6.67 times 10 to the minus 20 and 4th root. Okay, so if your calculator doesn't have a 4th root on it, maybe it has a y to the x, or let me see. Got a calculator I can look at. See what yours looks like. Let me see. Okay, there's square root, there's square. Oh, you can cube root. There it is. Right here. That right there. Okay. Yeah, that shift. It has the ability to do the 4th root. Let's see if yours does. Yeah, the X root. So you can do it there. Mine doesn't have that. So what I have to do is use my Y to the X key. And if you ever find yourself without those calculators, you can say it's the same thing as 6.67 6, 7 times 10 to the minus 20 to the 1/4 power. So I would punch this number in, and then I would punch 0.25 for 1/4 and hit the y to the x key, which is what I need to do now. So let's see, 0.25 and then hit this key right here. 1.61. So S equals 1.61 times 10 to the minus 5 molar. Well, they chopped it off to 2. Should I have done that too? Yeah, I should have. 2 significant figures. Okay. So that's how you calculate the solubility if you know the K value. And I need to go back the other direction. Calculate K if you know the solubility. I think that's what we're up to next. Well, actually, no. We're going to compare solubilities in not water solutions, but acidic solutions. So if we have silver chloride, probably shouldn't have erased it, but silver chloride solid, we want to put it in solution. And we want to know what impact the addition of nitric acid has on the solubility. I mean, intuitively, you would think, oh yeah, we'll add some acid, we'll get it in a solution. Well, you won't. Why? Because here's what nitric acid does. Right? It breaks up completely into these ions. Okay. All right, what can react with what? Well, there's none of this left. So we say, okay, if cation reacts with anion, right? Hydrogen plus chloride, what are you going to get? Nothing. Because HCl is a strong acid. It's already like that, and it wants to stay that way. So there's no reaction there. Nitrate and silver ions, same thing. Silver nitrate is completely soluble, right? So you don't get any precipitation there at all. You don't get any reaction whatsoever. So the addition of the acidity of the solution based upon nitric acid will have no impact on the solubility whatsoever. This is another way to look at it. Just add them together. There's the overall reaction. That is annoying. And I don't know how to stop it. Because it's not flashing up there, I think it's with the projector. Maybe the bulb's going out. I hope that's the case, because that means that the video recording will be good. Okay, that's what another way of saying this is this has no common ions between this added component and this reaction of interest. There are no common ions between the two, so it won't affect the solubility. What about silver phosphate? All right, let's change this to a silver phosphate. All right, and we should have 3 of these and 1 of these. It's solid, and then we need a phosphate over here. And we need 3 of those. Okay. What effect will this have on the phosphate, silver phosphate solubility? Well, even though we don't have common ions here, we do have the potential for reaction. Still silver and nitrate, right? They're not going to do anything. But according to Le Chatelier, all we have to do is reduce one of these over here, and it'll draw more of that into solution. So the only possible reaction is hydrogen and phosphate. All right, so remember this where we had, let's see, in the last chapter. H2PO4, 1 minus. I'm going to leave out the aqueous part just for convenience. Then we can take that one and it will dissociate a hydrogen, PO4, 2 minus. And then we can take that one, HPO4, 2 minus, and dissociate the last hydrogen. Okay. And remember, all of these have an equilibrium constant that's less than 1. And it gets smaller as you go down. So that means these are all weak acids. So a weak acid produces a strong conjugate base, which means it's going to be hunting for hydrogens. This is going to latch onto these hydrogens, or these hydrogens are going to latch onto that phosphate and take it back to here. And then this is going to latch onto some more hydrogens, as long as there's some there, make that. And then that's going to latch on to hydrogens come out here. Right? So what you're doing is, with this hydrogen, you're depleting this side of the reaction very effectively. And that draws the equilibrium in that direction and solubilizes the silver phosphate. So acidic solution will, a nitric acid will solubilize more silver phosphate. Now, just for argument's sake, what if we instead we say, okay, we just need hydrogen. So let's say, let's make it hydrochloric acid. What's going to happen then? Well, you might use up some of that, but the chloride would react with silver. And it would draw this reaction that direction, but it also precipitate the silver, right? So you get this into solution, but you produce another precipitate with the chloride. So it's important, even though this is not part of the reaction, as it's listed, if we make it something that does react with silver, then we're in trouble. Or as, what was that, Ocean's 11? Don Cheadle, he came out of the sewers. You remember that movie? He came out of the sewers and he was telling the group that he can't cut the power so they can rob the bank, right? And he says, "We're in Barney." What the hell is that? That's an English expression. He says, "We're in Barney. Barney Rubble, trouble." So if you put chloride there, you're in Barney. Okay. All right, so we can proceed by converting this phosphate eventually into phosphoric acid. And when it does, all we need is sufficient hydrogen to do it. Okay. So what is the solubility of silver phosphate in water compared to the silver phosphate in acidic solutions like nitrogen? All right, let's see. We did phosphate before, didn't we? Well, excuse me. That wasn't the question. It wasn't the solubility, it's the K. The K value for this reaction is constant. Solubility may change, but the K never does. As long as the temperature is constant, the K is constant. So, what if we, all right, now I'm going to switch back to chloride. All right, so chloride. All right, there we go. All right, so if the KSP is 1.6 times 10 to the minus 10, KSP, this reaction, okay? And now we've got 100 milliliters of 4 times 10 to the minus third molar calcium chloride in solution. So now the ice table is valuable. Not that it wasn't before, but it's even more valuable now. So the solubility here is going to be S, but we've already got a concentration of chloride. Will the calcium react with anything? No, calcium chloride is soluble. But the chloride is a common ion to this reaction. So it's already got some chloride here, which means that even though there's no silver, it's going to move to a certain point and then it reaches equilibrium sooner because it's already got chloride there. It just needs enough silver to satisfy the conditions of the K. So how would we write that? Well, we're starting off with this much here, but we're starting off with 4 times 10 to the minus 3 molar here. Okay, so we are definitely moving to the right because there's no silver there. And we're going to get 1 silver here, and we're going to get a chloride here out of that molecule. Okay, so now we have this one, and we have 4 times 10 to the minus 3 plus S. So then if we set up our equilibrium expression, 1.6 times 10 to the minus 10 equals S. And then this one is 4.00 times 10 to the minus 3 plus S. Okay. We get, well, we factor these out. Just run your factor. You get 4.00 times 10 to the minus 3 times S, and then plus S squared, correct? Well, that's going to leave us with a quadratic. So we want to ask ourselves, is this solubility going to be high compared to what? Compared to S? I mean, compared to 4 times 10 to the minus 3. Well, what did we find before? 10 to the minus 5 was the solubility in water. Right, so S is definitely going to be, at a minimum, 2 orders of magnitude lower than that. It's not going to have any impact at all. So what we can do is simplify this and say it's going to be approximately S. Well, I was about to skip a step, but maybe I better not. Times 4 times 10 to the minus 3. So 1.6 times 10 to the minus 10 equals 4.00 times 10 to the minus 3 S. So all we have to do is divide both sides by that value. Divide this one by that value. Correct? 1.6 exponent here, and then 4 exponent minus 3. Divide. So I get 4 times 10 minus 8. Solubility equals 4 times 10 to the minus 8 molar. Oops. And that being correct, yeah, it's a lot lower than this value. So we could run the 5% test, you know, to be sure, but I'm convinced that it's going to be less than 5%. All right. Hold on a second. What did I do wrong? Oh, shoot. I hate myself for doing that. And nobody stopped me. When calcium chloride goes into solution at 4 times 10 to the minus 3, What's the concentration of chloride ions? It's 2 times that. All right, so what we need here is an 8 and an 8, 8. And a recalculation. 1.6 exponent 10 and 8 exponent times 10 minus 3. 2 times 10 minus 8. There we go. So there are the calculations, and I should have just let the slide do the talking for me. Okay, and just a point to make, 100 milliliters doesn't matter. The only thing that matters is the concentration. Why? Because this solid is in 100 milliliters. It could just as well be in 5,000 milliliters. Doesn't matter because it has no concentration value. That's why it's not over here. And it's not in the expression. Sometimes the volume does matter, but not in this problem. When we do the lab, the volume will matter because we're going to be titrating something with another, and the final volume is going to be different. It's going to be what was in there to begin with, what you added will change the volume. Okay, what's the solubility of silver chloride in calcium nitrate? It's the same. There are no common ions there. Right? So solubility is going to be 1.3 times 10 to the minus 5 if we calculate it for water. It's exactly the same. Okay. So if you have, here's an interesting problem, and the usefulness of our equilibrium expression allows us to determine whether or not, if we put ions, say, for argument's sake, if we put silver ions in solution and chloride ions in solution at very low concentration, are we going to get a precipitate? Well, the question there is best answered by calculating the Q. If you've got a concentration for silver and a concentration for chloride, then you take those concentrations, calculate the Q, which would be similar to the K, the same procedure, and compare it to the K. Compare the Q to the K. If the Q, we just stick with this example. Right? If the Q is greater than the K, that means that we've got too much silver and chloride in solution. So you will get a precipitate. But if the Q is less than the K, it means we don't have enough silver and chloride in solution. So we're not going to get a precipitate. Okay. That's all that means. And you can use this factor to sequentially precipitate, say, metal ions from solution. If you choose the right anion for each one and put it in there at a sufficient concentration, then you can selectively precipitate metals from solution. And that's one way that we use to separate them. Sometimes they separate in groups. In fact, most of the time they do, separate in groups, and then you have to take the group and do something else to it if you want to get the individuals out. We're going to look at that in just a minute. Okay. We call that selective precipitation. So all we're doing is selecting the anion, where we can precipitate the metals, select the anion, and then create the proper conditions that will cause the Q for certain of the metal ions to exceed their K, and they'll drop out of solution and leave the rest of them behind, because the Q for those ions is still less than their K. Okay, so we generally start off with low concentrations of the anion so that we can pick up the metals that are particularly insoluble at very low concentrations. Okay, so the example here is, say we have a solution of barium and silver. Barium and silver. Right? What are we going to precipitate them with? Hydrochloric acid. So we want the reaction then, I'm leaving out the aqueous part. The reaction then produces barium chloride. Here, let's see, we need 2 of these. Because barium is an alkaline earth, so it's a +2 charge. And then silver is like this. So we have these in solution, and we're going to add chloride to them so that we can precipitate them. It's important that we only use the anion, and we don't contaminate our mixture with another cation like sodium. Sodium chloride will contaminate what's left over. Silver chloride, if we add HCl to this solution, will precipitate silver chloride and leave barium chloride behind. Actually, barium chloride is soluble. Right. So this is selective precipitation, but if we only have these 2, then we add chloride, and this one drops out of solution, and this one stays in solution because, I mean, barium chloride is soluble. Most of the chlorides are soluble, except for, I think on that list we had 3 of them that were not soluble. And silver was one of them. So that would selectively precipitate. So once you still got all of this in one big flask or beaker, right? This is still going on. This drops out of solution. This stays in solution, right? How do you get them apart? Right? They're still in that mixture. It's easy. Just filter it. Just run it through a filter with a small enough pore size to catch the very finely divided silver chloride, and it's held on the filter, and the rest of it goes through. Now, you're going to get some of these going through with the barium, right? Because we already know that this has a given solubility, but 10 to the -5 molar, right? But most of it is going to drop out of solution. And so you still, it's not the best scenario, but it's better than the alternative. It's kind of like, was it Winston Churchill? He said, democracy is the worst possible political system, except for all the others. Okay, so here we've got a mixture of copper 2+, mercury 2+, nickel 2+, and manganese 2+. And we're going to use hydrogen sulfide to selectively precipitate one or more of these out of that solution. So how do we do it? Well, at a low pH, acidic pH, the concentration of sulfide ion is very low, right? And that's probably on the slide, but I'll show you why here. So if we put hydrogen sulfide in solution, right, it's going to set up an equilibrium with this plus that. in aqueous solution. All right. So if we want, and it'll be a certain concentration here, but for our purposes, it's too high because with this much sulfide in solution, you would precipitate everything. All of these sulfides of those metals are insoluble. So what we want to do is decrease the amount of sulfide so that it'll take out the ones with the lowest solubility first. And then later we'll increase the sulfide concentration and it'll take out the others. Okay, so how do we do that? Well, if we add, let's see, low pH, tell us what we're going to use for. No, it doesn't. Okay. So if we add more hydrogen here, somehow, then it drives the reaction back this way and decreases the sulfide concentration. Right. I put the overall reaction here, but this slide shows you that, let's see, that you actually have a two-step deprotonation here. The first one, there's the first proton comes off at 10⁻⁷, and the second one comes off 10⁻13, just like we learned in chapter 14, 15. And the combination of the two, the overall K for that reaction is 10⁻20. So the concentration is very low. The K is very low for this. And we want it to go even lower. I mean, we don't want the K to go lower. We want the concentration of sulfide to go lower. We want the equilibrium position to shift to the left. So what we do is decrease the pH to around 2. So we give it just enough hydrogen ions that it will suck some of this off and leave a very low concentration here. Okay. So now we're sort of mixing quantitative and qualitative together. It used to be, when I was in college, chemistry was taught two ways. You had a qualitative chemistry class and you have a quantitative chemistry class. And they just went through, actually it was mostly lab work in the qualitative. Like we do flame tests, trying to identify unknown metals. We do these types of precipitations and selective precipitations, and use color and use any kind of qualitative indicators to analyze a solution or a sample, like kind of like being in forensics. And then the quantitative class, you would actually run the numbers. And yeah, that's enough said about that. So what we want to do is increase the pH, so we decrease the sulfide concentration. And if we do that, then we can precipitate out mercury and copper sulfide. We get mercury and copper first at pH 2. We get the mercury and copper. Okay, then we increase the pH. We add hydroxyl, and we increase the pH to, I don't know, does it say? Just a high pH, maybe greater than 8, probably. Then we can drop out the other two, nickel and manganese. Because now we've increased the amount of sulfide so that the Q value for these is now exceeds their K value. The K value for these is higher than for those by several orders of magnitude. And this will be a flow chart for doing it. Oh, that was a good guess, pH 8. So you would take out, you would get these first two out at pH 2, and then all you have to do is just add hydroxyl It's kind of tricky though. You don't want to add hydroxyl in the form of any of these ions, and you don't want to contaminate with other metals like sodium, but you might have to. And I'll show you why on the next slide. I think it's coming up. So this is too small to see, but this is a flow chart that incorporates what we just learned about the sulfide for separating this cocktail of cations, of metal ions. And notice they're grouped by, they're color coded. First group here is the one that will be taken out first. Then this one will be taken out second, this one will be taken out third, fourth, and then finally you have that one left at the bottom. So it's easier to follow that way that we've got them color coded. So the first thing you're going to do is, actually you're not going to add sulfide yet. It's more efficient to acidify the solution first with hydrochloric acid. Then you get silver, lead 2+ and mercury 1 as the chloride. Remember, mercury 1 is like this. Remember, mercury is kind of squirrely. It's always 2+ charge. But if you've only got one of them, then that was 2+. But if you've got two of them hooked together, each one is 1+. Okay, don't ask me why. That's just mercury in solution. Okay, so we hit them with hydrochloric acid first and drop those out. So that's group 1. And then we add hydrogen sulfide, which is in this already acidic solution. And that means that the sulfide concentration is very low because it's acidic. And now we use that and it drops out group 2, which includes the ones that we've talked about before, the copper and mercury 2+. Okay, and some of those others. That's group 2. Then actually they do say add sodium hydroxide. Okay, so we add sodium hydroxide and increase the pH, and now the sulfide concentration is up and it drops out group 3. Group 3 includes aluminum, iron, chromium, zinc, nickel, cobalt, manganese, and 2 different types of iron. Oh, okay. There's an interesting point here. We've got hydroxide added there, plus we've got sulfide. So some of these metals drop out as sulfides and some of them drop out as hydroxides. That one iron drops out as both, right? You get some hydroxide and some sulfide for the iron. So you still got a mixture, but at least it's not as complex as it was to begin with. And then what's left? Well, we're going to get a few more. Now we're going to add sodium carbonate. Sodium's already there, so we might as well add some more. Sodium carbonate will take out barium, calcium, and magnesium carbonates. And what do you have left in solution? Well, you have sodium. Of course, you've got a lot of sodium, and that's a wash. You can't determine sodium because you've added sodium hydroxide, sodium carbonate. So forget it. You got to get sodium some other way. But you do get potassium and ammonium are still in solution. Now, how do you get those out? Don't ask me. All ammonium salts are soluble, so you can't do it that way. All potassium salts are soluble too. All sodium salts are soluble. So they're just in solution. So I would suggest if you want to get them in solid form, just evaporate the water. Oh, you can get ammonia. You can get ammonia by distillation. If you increase the pH, and the pH is already high. Oh, that's good. pH is already high. So you've got this in solution, right? But it's in equilibrium with this one. Plus water. OH minus. Okay, so it's over here. It's got a lot of these and probably a lot of this. So what you want to do, no, having so much hydroxide in solution actually drives the reaction back here. So you've got a lot of this in solution. So now all you have to do is boil it. Boil the solution. This will come off, whereas sodium and potassium will not. Right? It takes too high a temperature to get them off. But this one will come out of solution, and as this one distills off, more of this is going to go back that way because you're removing this. So this distillation will then carry it over, and you'll condense it, right? You have a water condenser, and it'll drip out here into your Erlenmeyer flask, and then your Erlenmeyer flask, you have boric acid. And that acidic solution will keep it from revolatilizing as ammonia. Right? It's got enough acid in there that it will convert this to that as soon as it hits that solution. We used to do this all the time in soils or plant tissue to determine nitrogen content, because nitrogen is basically protein. If we wanted to know the protein in a forage, we would run this. We'd digest the forage in acidic solution, and then we would add base to it and distill it, catch it over here, and then you could determine the ammonia by some other means. Usually, let's see, what was the name of that test? I can't remember. But it's a color. It develops a color. And you can calibrate the intensity of the color to the concentration on the chart, and then just stick it in your colorimeter, and there you go. There are other ways to do that, of course, but this is one way that we did it. And this is actually the standard. This is called Keldal procedure. And then once you've got your other instruments standardized to this one, the original, then you're off and run it. I used to have an instrument where we would actually take the sample and drop the solid sample, ground up forage, say, into a furnace with extra oxygen. It would completely gasify it, and it would turn it into water vapor, carbon dioxide, and nitrogen gas. And then we would go through separate trains and detectors, and I could tell you how much nitrogen's in it, how much carbon is in it, how much carbon, nitrogen, hydrogen. Oh, I've got something else. Water gives me hydrogen and oxygen. Yeah, okay, oxygen. Anyway, I digress. The point is, this is not just academic. Okay, you actually do something with it. And depending on what you're interested in, right, you can branch off at any point. All right, so solubility. We talked about increasing the solubility by adding an acid. And that only works if if you take the solid, right, and it's going to produce this and maybe that. If the solid produces ions where the anion is a strong conjugate base, right? If it's a strong conjugate base derived from a weak acid, right? That's not a weak acid, but in our mind experiment, this would be the result of the solution of a weak acid produces a strong conjugate base. So if it does produce a strong conjugate base, then you can add some hydrogen ion to it, drop it out, and drive the reaction to the right. Okay. But if this is not, if this is a weak conjugate base, acidifying won't do anything for you. Right, so we need another approach. Instead of attacking that one, now we're going to attack this one. Get this into solution by converting that into something that removes it from that equilibrium. And that's where we form the complex ion. So you just have something down here with some anion, or it could be neutral. In fact, lots of times it is. And you form a soluble complex that removes it from this side and it drives the reaction that way. So that's what we're going to do next week in lab. We're going to form a complex ion. And the complex ions that form also have their equilibrium constants. Right? So if you have an A plus your complexing agent, right, it sets it up like this, and they're all in solution, but we still have a K. And in this case, the K equilibrium includes all of them because they're in solution. Right? So you would have AX divided by the A plus. Well, I can't say that. Let's just say A. Like that. And that would give you an equilibrium expression, and you can pick and choose. And actually, you can combine this reaction with the other one. Just Hess's law, right? Just combine the balanced equations and find out what the overall equilibrium constant is if you want to run that complexation. Okay, so I think it'll make more sense if we do an example. In this example, the complex ion that we're forming is with the beryllium 2+. Yeah, beryllium, it's an alkaline earth. Beryllium 2+ ion. We're complexing with fluoride ion. And we've been able to determine that the stepwise, right? This is just like acid-base reactions or acid dissociations. It happens in steps, right? So we get one fluoride with this equilibrium constant driven far to the right. And then we get that one and we add another fluoride, it's far to the right. Add another fluoride, it's far to the right. Add another fluoride. So we get 4 fluorides. And balancing the charges, our complex ion has a 2- charge now because we have 4 minuses and a 2+ here. So overall it's 2-. Does that make sense? And the overall reaction is this beryllium is complexed with 4 fluorides to yield the, let's see, for anions, tetrafluoro beryllium 2+ ion. Let me see if I named it right. You have a different naming convention for negative ions and positive ions. Let's see. I just give you examples. Okay. Hexafluoro cobalt. Okay. So this will be tetrafluoro berylliate with a 2+, with a Roman numeral 2 behind the beryllium. Okay, but if we combine all these, how do you get the overall K? You multiply them together, right? The final K is K1 times K2 times K3 times K4. So the overall will drive the reaction all the way to this complex ion with 10 to the 12th power of the K. So it's going way to the right. So if you want to get a beryllium compound into solution, this would be a good way to do it. Just add enough fluoride. Actually, it won't take much. And you can drive that reaction all the way to the right and get beryllium, your beryllium salt into solution. Now, whatever beryllium is combined with, the anion, you may not care about that one. Maybe all you want is the beryllium metal in solution to do something with it. That's a possibility. Okay, so to recap, there are two strategies for solubilizing in aqueous solution and an insoluble compound or a slightly soluble compound. One is acidify it. Right? If the anion is a good base, is a strong conjugate base of an acid like silver phosphate, then you're in business. Just acidify the solution and you can go to town. If it's not, then you need to form a complex ion with the metal, with the cation. And that's what we do with silver chloride. We want to get silver chloride in solution. I think the next one. Oh, good. We got Saul Kahn wants to talk to you.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So for losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus, raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. So we put in here 1.8 times 10 to the negative 10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 to the negative 10. So we take the square root of that, and X is equal to 1.3 times 10 to the negative 5 if we round that. So X is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver +1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver +1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver +1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening. All right, so we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right? We have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those 2 reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add 2 reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those 2 reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative third. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia. So let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here. So we leave silver chloride out because that's a solid, right? But we have ammonia. So this is all over the concentration of our reactant. So this is over the concentration of ammonia. And notice our coefficient is a 2. So we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is x, and our equilibrium concentration of chloride anion is x. So on the right side, we would have x to the first power times x to the, let me take that out, times x to the first power, right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. All right, so we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x is equal to 0.14 molar, right? So that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride, right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
So if we want to solubilize silver chloride by forming a complex ion with the silver +1 ion, ammonia is a good way to do it. So here's the one we want to solubilize. If we want to do this, silver +1 and chloride. Okay, we want to take that silver and we want to complex it with ammonia. Right? And this occurs in steps just like the fluoride did. So we have an equilibrium set up here where we're going to have silver and ammonia, and still have the +1 charge because ammonia is neutral. This is aqueous and this is aqueous. And this one has a K of some kind. And then we take that other one and it will accept another ammonia. And this is the one we're after. It's still a +1 charge. And that has a K. Okay. Right. This K is K SP equals 1.6 times 10 to the minus 10. And that first one is 2.1 times 10 to the third. So it's way to the right. And this one has 8.2. 8.2 times 10 to the minus 10 to the third. Okay. So it's way to the right. But what we're interested in is overall. How can we improve the solubility of this one if we add all these together and multiply those three together to get our final K? That's what we're going to do. Composite the three. Yes, this is the true situation in solution because all of these are in there together. Right. So overall is what we're really interested in. All right. So when we add them together, that means this one cancels. And lift out the plus. This one cancels. So we've got silver chloride, solid, 2 ammonias, right? One here, and that yields the complex ion in aqueous solution plus chloride. Okay, that's overall. And the K for that is 2.75 times 10 to the minus 3, is it? Yeah. So that may not seem like much, but when you compare to this solubility, compare that K to this K, you've improved the K by a factor of 7 orders of magnitude. Now, to really know what improvement in solubility you have to run the numbers. Right? Take this as our overall, right? And set up your ice table with the values that you have for ammonia concentration in solution, and then find out what the solubility is. Okay. So there's your expression. So this one times that one divided by this one, right? And that one drops out, is that K. Okay. Okay. And since this is, since we've got, let me do it this way. Since we've got ammonia in the denominator squared, and we want, we want to increase this concentration as high as we can, then this usually is a very large number, like 1, 2, 10 molar. 10 molar is not uncommon. So you put a lot of ammonia in there. And if you put a lot of ammonia in there, here, it drives the reaction that way. Right? Once it's in equilibrium, you're going to say, all right, more ammonia, more ammonia, more ammonia. It keeps driving it this way, taking this, putting it in solution. So we increase the concentration of ammonia to satisfy Le Chatelier and get everything into solution. And you'll usually have a lot of that left over, so much so that you can smell it. Okay. So here's the ice table based upon this reaction. I'm going to let the slide do my talking for me. Because we're going to do it again when we talk about the lab. So I'll save my writing till we do the lab. All right. So if we start off with 10 molar, they didn't tell us that, did they? 10 molar ammonia. Right? So we're going to have 10 molar here. There we go. And we want to get more of that in solution. Well, of course, there's 0 to start with. Then we're going to drive it that way. We're going to lose some. Now, remember when I mentioned earlier, I think in chapter 13, when you're doing these ice tables, if you can pick the unknown, so that solution of the problem, the unknown solution will give you the answer you're looking for. So we say, they're using X, I like to use S. So if the solubility here in this scenario will give you, actually, will take up 2 of these. For every one of those, you lose 2 of these. Right? I guess I will have to do the ice table. So for every one of these, you need 2 of those. So we're going to lose 2 of those. And we're going to gain 1 of these, right? Plus S. And we're going to have 1 of these. Okay. So overall, now we've got 10 minus 2S and S and S. So now we just solve the equation like we did before. Right? They're filling the values. They're using X's. I'll modify that slide and put S in there. Notice we got a square down here. Let's see, right there. So how are we going to deal with that? Well, the nice thing about that expression is, let's see. This KEQ is equal to S times S. Let's do it like this, like that, like that, like that. Like this, 10 minus 2S. And this is going to be squared because this is ammonia. Here we go. Two of those. That's squared. But look at this. This is actually S squared. So now we can pull the square outside. So we have S on top, 10 minus S, 2S on the bottom. And the whole thing is squared. So if we have a value over here, 2.75 times 10 to the minus 3, then we can take square root of both sides. So this one divided by this one is actually the square root of 2.75 times 10 to the minus 3. So we don't have to estimate. Right? We don't have to get rid of that X. And that's good. So the next slide gives us the solubility. Why is it doing that? Oh, okay. Yeah, there are multiple steps. Sorry. But eventually, when we solve for S, we find that it's 0.47 molar solubility. So the solubility of silver chloride now, with this much ammonia, is 0.47 molar. That's quite a jump from what, 10 to the minus 5? Quite a bit. Just by putting in 10 molar ammonia. Okay, so like I said before, you got a lot of ammonia left. So if we solve this expression here, right? Put our X in there, then we find out how much ammonia is left over, because that's the expression for here. This is how much ammonia is left over at equilibrium, right? So we've only used up 1 molar, and there's 9 molar left over. But we need that for the equilibrium to be favorable. It stopped flashing. Why did it do that? Spoke too soon. Okay, so that's it for the Chapter 16 lecture.